Okay, so let's continue. Last time we defined this real-time finite temperature Green's functions, and we could decompose this gxt into this g greater part and g lesser part as we defined earlier for this single particle zero temperature Green's function. And we could Fourier transform this gxt to gk omega in this Fourier space, and by this kind of a spectral representation of this gk omega, we could expand this, this Fourier transform this thermal Green's functions in terms of this eigenstates of this Hamiltonian and the momentum operator, right? So it's the simultaneous eigenstates of your Hamiltonian and momentum operator, and this m and n represents this eigenstates of this simultaneous eigenstates that we use to express this gk omega. And then by the end of the day, we found that this is given by this combination of the thermal factor divided by this energy denominator. Okay, so the energy denominator is this omega minus this km minus km. Remember, this km minus km represents this kind of excitation energy, which is the energy difference between the states m and n. Okay, and this number n and m represents the total number of particles, and we know that this residue is actually this matrix element square, which is the 5, sandwiched by this Dirac-Brock state m and cat state n, and this matrix element square vanishes unless this number of particles in this state n and m differ by 1. Okay, and so this gk omega shows a simple pole right at here when this denominator vanishes. So you have two different kinds of this simple poles, which is km minus kn divided by h bar plus minus I eta. In terms of the energy eigenvalue, this is the energy difference between this m particle and m particle states, and this is the chemical potential difference, and you get a plus minus I eta, which is the above and below the real axis. Okay, so we will come back to this later, but let's just assume that we could perform such a calculation, and we could further decompose this energy denominator 1 over omega plus minus I eta into two parts: the real part, which is the principal value of 1 over omega, and the imaginary part minus plus I pi times delta function. So this is from the Cauchy theorem, right? Cauchy's principal value theorem, which allows us to decompose this 1 over simple pole energy denominator in terms of the principal value integral, which is the real part, and the imaginary part, which shows the delta function. So you could go back to your applied maths and look for the Cauchy theorem, and you know that this is the identity. So you can plug in this Cauchy's theorem back to this simple pole, and you could derive the full expression, which separates the real part from the imaginary part, and you get this expression here. Okay, so the real part contains the delta function, which conserves the momentum and is residue, and also thermal factor and the principal value, and there's another thermal factor right there, and minus plus this imaginary part. Okay, so you could also just separate this imaginary part, which is the minus I pi delta part, and you could simply just separate this imaginary part. So this imaginary part is very important because this is going to be the thing that you measured in your laboratory, because this is proportional density of states. Remember, we already defined this quantity rho, which is proportional minus this imaginary part of the Green's function, right? So this is the finite temperature generalization of such a imaginary timed Green's function, and you could check that there is a relation between the real part and the imaginary part of the Green's function. So, and this is your homework problem, so you can verify that if you just write down this real part of the Green's function and the imaginary part, and you find that there is a relation between these two. And this is what I mentioned earlier, Kramers-Kornick or KK relation. Remember, at 0 temperature, we have a similar relations between the real part and the imaginary part of the Green's function. But at finite temperature, we have a similar relation between the real and imaginary parts, except now you get the thermal factor, hyperbolic tangent of beta omega prime divided by 2 with the power plus minus 1. So at 0 temperature, beta goes to infinity and hyperbolic tangent goes to 1. So you could actually cross this hyperbolic tangent factor out because this is just 1. Okay? When temperature goes to 0. And then this is precisely the KK relation at 0 temperature that you are familiar with. But at finite temperature, this factor should actually multiply by the thermal factor, hyperbolic tangent. And so you could check yourself that I don't want to assign this to you as a homework problem, but you could convince yourself that there is a thermal factor here and there when you actually rearrange those terms by plugging this residue and the Cauchy's theorem. Okay? Great. So this is just a simple algebra, but we will come back to this quite soon. So far, this is just a general formulation of this real imaginary part of the Green's function and in k and omega space. And we know that this is the imaginary part of the Green's function is related to the tensor states, and this tensor state is what you measure in the lab. But the problem is, how do we calculate this thing? Well, the answer is that we cannot calculate this unless we take a detour, we go to the imaginary time Green's function, and we define this Green's function in the imaginary time domain. And then we can actually define a similar object like the real part of the italic and imaginary part of the italic Green's function. So then we will relate this to imaginary part of the Green's function. And the relation between these two is that both functions are defined through this density of states. Okay, so you have the same density of states, but you can define this in different basis. One is the real frequency, another is Matsubarra frequency. So we need to take the analytic continuation to go from imaginary part or imaginary frequencies to the real frequencies, and this is the detour. Okay? So there is a way that allows us to compute this thing, and then we can actually convert the imaginary frequency to the real frequency, and this is what we want. Okay? Good. So let's take a short break. When we come back, we will continue defining this retarded and advanced Green's function at finite temperature. So it's a bit technical involved at this point, but it is a necessary complication. So once we overcome these technical complications, you get a better idea what we are trying to do and also what we can do on the theory side. So you could check its references that are listed, for example, this Flansburg or Fetavlachka or the Nagel and Oland. Okay, so these formulas are easy to find. So next we will try to define this spectral density that we already defined for 0 temperature Green's functions, but here we should define this at finite temperatures. But before that, we will define this retarded advanced Green's functions. Okay, so as before, we could define this retarded and advanced Green's functions at finite temperature following this definition of 0 temperature retarded and advanced Green's function, except now we have this thermal factor, right? So this rho represents the density matrix, which is, remember this factor right there. Okay, so this is called the density matrix, which is the thermal factor e to the minus beta k divided by the partition function. So it is more convenient to express this Green's function in terms of this rho rather than just this partition function, which looks a bit messy. But in any case, as we defined already, this retarded advanced Green's function is related to the commutator or anti-commutator between the psi and psi dagger at two different space and time coordinates. And this minus sign refers to the commutator and the plus sign for this anti-commutator. Of course, this minus sign refers to the boson, and the plus sign for fermion. Okay, so the advanced Green's function is defined a similar way, except that now we have this minus sign in front, and the theta function is the same. Okay, so remember, previously zero temperature, this retarded Green's function shows the pole, simple pole, below the real axis, while this advanced Green's function shows this poles above the real axis. And here is the same thing, except now this residue corresponding to this pole shows the thermal factor. So that's all.
And the second thing is, I'm curious, before the trace, in general, we will the trace divided by the partition function. But now that the partition function can put inside.
It doesn't matter because this partition function is just a number. Good, so let's take a Fourier transform. But we have this minus sign already. So this G retarded. Okay, so you can recognize that this spectral representation of the retarded and advanced Green's function looks, at finite temperature, looks really similar to this zero temperature counterparts, except now you get this non-trivial thermal factor in front, here and here, and also the advanced part you get a similar thermal factor. So, but the pole structures are really the same, so you have the simple poles when this denominator vanishes, and this happens for the advanced Green's functions below the real axis because this is plus I eta, and for advanced Green's function this occurs above the real axis. So we got many simple poles for G advanced above the real axis, and for retarded below the real axis. And the residue is just this matrix element squared times the thermal factor. Okay, so I believe that you are able to use this G less and G greater decomposition that we introduced earlier to actually convince yourself that the G retarded and G advanced shows such a K omega dependence. So this G retarded and G advanced Green's function are analytic in the upper or lower half plane. Meaning this is the complex plane Z, which has this real frequencies in the x-axis, but the pure imaginary, along the y-axis. So you can see that this G retarded shows the simple pole below the real axis, which means that there are no poles above the real axis, which means that G retardeds are purely analytic functions. By saying analytic, I mean there are no singularities. There are no singularities above the real axis for G retarded, and advanced is the opposite. So it is analytic below the real axis. Okay, so this turns out to be a very important properties for later purposes when we perform analytic continuation. So let's just define the spectral weight. So like before, we can define the spectral functions from the real Green's function. So if I define this rho K omega like this, then I can just simplify this G retarded and G advanced expression in terms of rho. So G retarded is this, and G advanced. Okay, and the imaginary part of the Green's function for retarded is minus 1/2 of rho, and for advanced it is plus 1/2. Okay, so everything is almost the same except we have the thermal factors put in at finite temperatures. So this is the full expression of this Green's function in Fourier space at finite temperatures, and ideally this is what we should calculate, and this is what we should measure in the lab. Namely, everything that related to measurements is density of states, spectral density or spectral weight. This is a measurable quantity, but then the problem is that we cannot calculate this, if we stick to the real-time, real frequency Green's function. So we need to really calculate this first. The way that we calculate this is that we will generalize this G retarded and G advanced to the complex plane, and then we could make an analytic continuation from this purely imaginary axis to the purely real axis. And then, the spectral function is actually the same. So let's take a short break. When we come back, let's just define this generalized function called gamma, which is the generalized form of the G-retarded G-advanced in the complex plane. So let's define so-called auxiliary function, gamma, in the complex frequency plane. So this omega is omega prime that we just defined. And z is a complex variable which has the real imaginary part. It's like our omega. So the G-retarded and G-advanced that we defined earlier corresponds to this boundary value. Namely, so this is our complex z plane, and we could define this gamma in this general complex plane. And then we could take some kind of a continuation, and this continuation from above or from below to reach the real axis. If we take this kind of a continuation from above, then we could define the G-retarded. Because remember, the retarded Green's functions shows the pole below the real axis, right? And so there are no poles in the upper half plane, right? So we are able to simply just take a continuation, so-called analytic continuations from any points in the complex plane to actually approach to the upper real axis. And if we approach this from below, and we can define G advanced. So this is called analytic continuation. And this is a very important point which allows us to link this imaginary Green's function to the real Green's function. So G-retarded G advanced Green's functions represents the boundary value as z approaches the real axis from above, which corresponds to G-retarded, and below, which corresponds to the G-advanced. Okay, so this is what we would do. So we will define a more general kind of auxiliary function, which we call this gamma, and this gamma is defined in the complex z plane, right? So z could go from the real to complex to pure imaginary value. And fortunately, the G-retarded function shows no pole at upper half plane, so that this gamma function can actually go analytic continuation from any place in the upper half plane to really almost touch to the real axis. Okay, and you could also approach this from below, and then you can find that this gamma function is really this kind of boundary value of the gamma function really corresponds to this G-retarded and G-advanced components of a Green's function. Okay, so, and this is a trick, and this is a very good trick that we can play. So we could define this density, spectral density for fermions and also for bosons. For fermions, this quantity rho is always positive. Definite for bosons, rho times sine omega should be positive definite. And this includes all the information we need. And then we will take a detour, as I mentioned earlier, that take us from the imaginary time Green's function to the real-time Green's function. And the link between these two is the density spectral function. And we will take advantage of this gamma function for such a generalization. Okay, so let's just describe this procedure for this analytic continuation. So first, we could compute the temperature Green's function, imaginary time, biospectral weight. And remember, this is G italic. okay, and at Matsubar frequency, which is, imaginary frequencies, I times this omega n. Remember, this omega n refers to this 2n pi over beta for boson and 2n plus 1 pi over beta for fermion, right? So, and we also define the spectral weight through this imaginary time Green's function in the Matsubar frequency domain. Remember that. So this is given by this integral over omega prime, right? Okay, so if you go back to your earlier note, this Matsubar frequency representation of this Green's function, then we can define this spectral function, right? So, which is the imaginary part of the imaginary time Green's function in the Matsubar frequency domain. So, we could calculate this thing because we are able to calculate this thing, right? So we can compute both the real imaginary part of this Matsubara Green's function, and then we extract the imaginary part, and then we get the real part. And then we could then take a detour by defining an analytic continuation, meaning we can define the kind of a auxiliary function, the gamma function over there, and we can define this as a gamma function, right? And we can generalize this, say, Matsubara Green's function to gamma function, which applies to everywhere in this complex Z plane, right? Okay, so, and Z in this generalization could be a real value or complex or pure imaginary. So imagine that this is in general a complex variable, then we could just assign this gamma function from the purely imaginary axis to all the way to almost the real axis. Because when Z is actually the Matsubara imaginary frequency I omega n, and this gamma function is the same as the imaginary time Green's function in this Matsubara domain. So, in other words, if I simply just define my gamma functions right at this vertical y-axis, which is a purely imaginary axis, then I go back to the gk I omega n. But this is what I can calculate, but this is not what I want. What I really need is capital G. It's not italic G. But what I can do is that I can define this gamma function, which is analytical through this complex plane, and I can just analytically continue this gamma function from this purely imaginary axis to almost the real axis, because there are no poles right there. So, in other words, when I do so, this is nothing but when Z goes to omega plus I eta, and this is my analytic continuation. So when Z goes from I omega n to omega plus I eta, I go from italic G to capital G, retarded. Okay? So likewise, if I start from the negative imaginary axis, and I could actually do the same thing by allowing the Z goes from I omega n to omega minus I eta, then I go from G italic defined in the purely imaginary axis to G advanced, capital G. Okay, so, and this is the detour I mentioned many, many times, and finally we got the complete picture. What I'm trying to say is this mapping between imaginary and a real axis of a same function. Gamma function is the same function, but it corresponds to G italic along the vertical imaginary axis, and it corresponds to G retarded advanced in the real axis. You get that? So the next is a remark that we cannot calculate the G capital or the real-time Green's function directly. We need to go the detour. We could compute so-called temperature Green's function or thermal Green's function or imaginary time Green's function first, and then we could relate G italic to capital G by analytic continuation. Okay, so the key point is that this rho, the density, spectral function density, could be computed through the G italic, and then the same rho that we defined, in this imaginary time axis is the spectral function for the real Green's function. This is capital G, meaning the rho actually is the same in both representations. Okay, so rho is actually minus 2 imaginary part of this G italic is also the same for G capital, right? So we should first compute the G italic in imaginary time, the thermal Green's function, and then we use this spectral function that we calculated through the G italic, and we plug into this formula, and we get the imaginary part of the retarded advanced Green's functions, where this omega is really a real value. Okay, so meaning when I do such a identification, I use this analytic continuation that we just defined by defining I omega n goes to omega plus or minus I eta, where plus refers to retarded and minus for advanced. Okay, so this is what we really should do, and the steps that we should really go through is that we first calculate G italic, and then we find the spectral function to plug in to this capital G retarded advance, and by such an continuation, by setting I omega n to be the real value, omega plus or minus I eta, and then we go from G italic to capital G. Okay, so time is up. I think this is a perfect time to stop for today. So I hope you now get a complete full pictures of what we can do and cannot, and please read the corresponding section chapters in our references, and I'll see you on Wednesday.